Now we will talk about the zero-sum sets. Here zero-sum means there's a zero modulo something, or zero modulo n, or modulo p. Right. In the discrete math course, there's some exercise of this type. So if a1, a2, a n are integers, then there exists a non-empty subset I of 1 up to n such that the sum of the AIs is divisible by n. Do you know the proof? If you don't know the proof, you can stop this video for a while and think of the proof and come back. So the idea is to use the Pisonal principle. Think of these n numbers. If any one of them is a zero modulo n, then we are done. So we can assume that none of them is zero modulo n. Then two of them will be equal by Pisonal principle. Then you subtract them, and the remaining is a non-empty subset whose sum is divisible by n, right? Zero modulo n. So that's easy exercise. But what about, so we want to generalize this further. So the question is, can we always find a subset I of size precisely n so that sum of the AI is divisible by n? So I mean, of course, if you only have n numbers, this doesn't make sense. But what if you have many numbers? What if you have more than n but some numbers? And here's one example. So you have 0 n minus 1 times and 1 n minus 1 times. In this case, no matter how I pick the subset of size n, their sum is never a multiple of n, right? So here you have 2n minus 2 numbers, and you can never make a multiple of n by selecting n of them. So with 2n minus 2, it's impossible. And this theorem, due to Erdős and Ginsburg and Ziv in 1961, says that 2n minus 1, with 2n minus 1 numbers, this is possible. So every sequence, okay, I should say, what is the best formulation? If a1, a2, a2n minus 1 are integers, then there exists a subset I of size n. That's important, otherwise it's trivial, such that sum of the corresponding numbers is divisible by n. All right, so that's the theorem. Now I'm going to show you several proofs, but before showing you any proofs, I'm going to first tell you that one can reduce this to a prime. So this is a claim. We may assume n is prime. Suppose not. So we're going to apply induction on n, right? Suppose not, and then n is m times p for some prime p, and m is bigger than 1. All right. Now, whenever I have a 2p minus 1 integers, then there's a sum p of them whose sum is divisible by p, right? So among all these n 2m minus 1 integers, I take these pictures. I choose 5 of them. I mean, not 5, but 2p minus 1 of them. Then there will be some p of them whose sum is 0 modulo p. And then let's take away and then add 3 more, and then I can select another 3 and then take away them and then repeat this process. So how many times can I repeat? Each time we are removing p of them, right? So if we repeatedly take a set of size p, okay, set I of size p with the property that sum of the ai in I is 0 modulo p, L times, then number of remaining integers is, initially we had 2n minus 1 integers minus each time we take away p of them, and let's say each time we take a p away, and let's say we so that L, right, and 2n is 2mp minus lp minus 1, right? So this is 2m minus lp minus 1. So as long as this was, if 2m minus lp minus 1 is bigger than or equal to 2p minus 1, then we can get one more II. So that means, so we may choose L to be what? The first time it's going to be smaller than that, right? So 2m minus, it's not, if it's minus 2, then it's minus 1, right? So that means, so we have 2m minus 1 disjoint sets, subsets I1, I2, I2m minus 1 of subsets of 1 up to 2n minus 1, such that the sum of ai in ij is 0 modulo p for all j. Now you have this 2m minus 1 set. Now we apply induction hypothesis again. Oh, by the way, I was already applying induction hypothesis. how do we take away this thing? Because P is smaller. P is smaller than N. So when you apply induction, we can assume that the Ginzburg-Gibbs theorem is true for this P, so we can take away such a set. Now, N is smaller than N, so I can apply induction over here as well. Then there exists J, which is subset of 1 up to 2n minus 1 of size M such that the sum of AI for J in I, right, sum of AI for I in J, no, I in IJ, where J in J. And then this is already multiple of P, so I divide by P, and still it's integer. This is going to be 0 modulo M. This is again by induction hypothesis. Because I'm assuming that the theorem is true for M. This means, so let's say K be the union of all IJ, where J is in J. Then size of K is equal to M times P, so which is in, and sum of the AI I in K is 0 modulo M, right? And sum of AI. So this implies that sum of AI. So when you divide by P, then it's multiple of M. So this is going to be 0 modulo N. All right? So that's why we can assume that N is a prime. So from now on, we may assume N is P for a prime P. Now I'm going to show you several proofs. So first proof using the permanent lemma. Okay, so suppose that A1, A2, A2P minus 1 is less than or equal to P and 0. I mean, because it's all about modulo P, I can assume that numbers are from 0 to P minus 1, right? So this is fine. And we may assume that AI is less than AI plus P minus 1. Why? Because if AI is equal to AI plus P minus 1, then all these numbers are equal. So otherwise, AI is equal to AI plus 1, that's equal to AI plus P minus 1. And their sum is a multiple of P. All right. Now, let J by P minus 1 by P minus 1, all one matrix. Let Li be the AI and AI plus P minus 1. And let's say B1, B2, P minus 1 with the list of elements not equal to minus A to P minus 1. Okay? you pick one and then all others. So modulo P. Right, and note that the permanent of J is, any permutation will become 1. So this is permanent is actually the number of permutations, which is P minus 1 factorials. This is not equal to 0 modulo P. So by the combinatorial, no, by the permanent lemma, there exists xi in Li so that I's coordinate is not equal to Bi. Alright, so what does that mean? That means we are selecting either, right? So this means that sum of, so this left hand side is a linear combination. Actually it's a sum of P minus 1 distinct AIs, right? And this is not equal to Bi, right? So, and this is not equal to Bi for, yeah, I shouldn't say AJs. For this is for all I, so that means this sum is equal to minus A to P minus 1, because that's the only term that is remaining. So this sum, so that means I have A to P minus 1 plus a sum of xi is equal to 0 modulo, so this is modulo P, so this is modulo P. Right? So that's it. So that's the proof. We found, xi is in Li, so we found the sum of the P element whose sum is not is divisible by P. Now our second proof uses Cauchy-Davenport theorem. So again, we have the same setup, and we may assume, right? We may assume AI is strictly less than AI plus P minus 1. So let AI be these two sets. Now we look at the this thing. By the Cauchy-Davenport theorem, this is at least P or the size of AI minus P minus 2. But this is 2, right? So 2 times P minus 1. So that's minimum P and 2 P minus 1 minus P minus 2, which is equal to P. Right? So this means that their sum covers every element modulo P. In particular, we can find A minus A to P minus 1. So there exists I So here, so one choice, so you take a one, A1 or A1 plus P minus 1, A2 or A2 plus P minus 1, etc. So you can choose one from each, and then their sum is equal to minus 2P minus 1, and that's the proof. All right. That was the second proof. Now I'm going to show you the third proof. The second proof, by the way, is the original proof by Erdős, Ginsburg, and Gibbs. And the third proof uses the Chevalier-Running theorem. Now we're going to consider two polynomials. Sum of ai xi p minus 1 is equal to 0. That's one polynomial. And the second polynomial is sum of xi p minus 1 is 0. Of course, everything is in modulo p. Right. All right. Now, number of polynomials is 2, and the degree is p minus 1. So the sum of the degree, sum of degree is 2p minus 1, which is less than number of variables, 2p minus 1, right? This is number of variables. So that means, and also x1, if we put everything 0, is a common root. And we know that the common root cannot be unique. So there's another common root. y1, y2, y 2p minus 1. All right. Now let's look at this. yi to the p minus 1 is 0. So what does that mean? That means this value, by Feynman's little theorem, this value is 1 if yi is non-zero and 0 otherwise. So that means the number of non-zero yi's is equal to 0 modulo p. And then, so that means, because we are talking about numbers from 0 to 2p minus 1, the only possible number is 0 or p. But it cannot be 0 because this is a common root other than all 0 vectors. So the number of non-zero yi's is precisely p. But now we know that ai times yi to the p minus 1 is 0 modulo p. So what does that mean? That means whenever this is non-zero, then this will become 1 modulo p by Feynman's little theorem. So that means sum of p of ai is 0 modulo p. Okay, so that's the proof. So this is a proof by using Chevalier-Running theorem. All right. There are also more proofs, but let me finish this subsection. I mean this thing about the Erdős, Ginsburg,